Hello, this is the presentation of my master's thesis about federated learning with multilayer perceptron models for sensor drift compensation in direct ethanol fuel cells. Alcohol was a contributing factor in 15% of all traffic deaths according to the European statistics in one of the previous years. Therefore, evidential breath tests are performed by breathalyzers to prevent traffic accidents. However, the breathalyzers tend to produce inconsistent results under intensive use. This malfunction is called sensor drift. The breathalyzers are usually equipped with ethanol sensors, like one presented on the picture. These ethanol sensors are also called direct-ethanol fuel cells. They convert chemical energy into electrical energy. This conversion is performed by oxidizing reactions presented on the slide. So the ethanol is oxidized on the platinum anode and releases electrons to the outer circuit, while the protons of hydrogen passes through the membrane. So the main malfunctions are caused by electrolyte evaporation. This is the strong acid in the sensor, by clogging of the pores of the membrane, for example, by smoke or by some particles, and the catalyst degradation, so the platinum surface can be destroyed. A typical output of the measurement is a voltage decay curve presented on the left slide, or the left picture. It is usually divided into two halves. The first half is the measured signal, and the last one is the extrapolation of that. This is done to speed up the analysis. The whole integral, so the sum of both integrals, is then mapped to the calibration line to get the concentration output. However, the malfunction described earlier cause the first part of the integral move to the second part, and therefore the whole analysis more depends on the extrapolation, and that results in the inconsistent results. So there are no data sets available on the internet, therefore the automatic sampling system was designed specifically for this project. You can see the workspace on the left. So the breathalyzer turns on air compressor that passes dry air to the breath test simulator that has a liquid sample of ethanol with known concentration. And then the humid gas goes to the breathalyzer for analysis. The breathalyzer then turns off and off the air compressor, and the second iteration starts, and so on. So the data set was collected for 8 different sensors for 3 concentrations, 50 measurements each. Therefore, that results in 1,200 data points. Each data point represents a voltage decay curve. Each data point can be described by 8 features and 1 label. So the features are the slope of the voltage decay curve called decay. Ymax is the amplitude. Tmax is the time when the amplitude occurs. Both the next features are the measured and predicted integrals respectively. The temperature of the area, the calibration coefficient, the intercept of the calibration line, and the concentration error measured by the difference between the measured and true concentrations. So you can see the comparison of 2 different sensors for the same concentration. The sensor on the left is new, the sensor on the right is very old, and the amplitudes are very different, and therefore the first sensor produces consistent results, while the second one is very inaccurate. The mutual information is calculated between the features and the label, and we see that most of the features are dependent with the concentration difference. However, the temperature is very low. This is mainly caused by the low variance of this feature in the whole data set. So I constructed an empirical graph from all the sensors by connecting each node, that is the sensor, with three nearest neighbors, and the distance is calculated by the Euclidean distance between the representation vectors that are the mean of all decays, the calibration coefficient, and the intercept. And then the similarity is calculated by scaling the distance by 1000 for simpler optimization. The local models are the multilayer perceptrons with the structure presented in the table. The maximum number of neurons in the hidden layers is 128. The activation functions, the first two activation functions are GELU, that are a bit more complicated versions of ReLU for nonlinear, for non-linearity. And the last two functions are 10H for the feature standardization. Also, normalizations and dropouts are applied at some hidden layers. And also the residual connection is added to the output. So these local models are optimized in a federated learning manner. And also the decentralized version of federated learning is used. So there is no server that aggregates the model weights. However, the local losses are regularized by the variations between the neighbors. So the variation is calculated as the squared Euclidean distance between the model's parameters. And the hyperparameters of the optimization process are presented on the left. And the main one is the alpha that is responsible for the similarity between the the neighboring models. And this is set to 0.1. The model evaluation performed as follows. So a test node is connected to the trained empirical graph, and it receives aggregated model parameters and calculates the tuned concentration. So measured concentration plus the output of the model with the aggregated weights from the neighbors. And then the method is considered effective if the true concentration, the absolute difference between the true and tuned concentration is less than absolute difference between the true and measured concentration. So let's move to the results. First of all, the training is performed for all sensors, and we evaluate the presence of overfitting or underfitting. And according to the table on the right, we see that underfitting probably occurs for the sensor 5 because the training error is a bit larger than the validation one. However, no signs of overfitting is detected. And also the fitting for the first two nodes is presented on the left as an example of sufficient fitting. Then the test sensor is connected to the train graph to aggregate the weights and calculate the tuned concentration. So therefore, the training process was done 8 times for all versions of empirical graph without each of the sensor, and the results presented in the table as the relative difference between the measured and tuned root mean squared error between the true concentration and measured and tuned concentrations. And we can see that some sensors perform very well, for example, the first sensor and the sixth one. However, sensors like 2 and 8 has a very low performance. This is mainly caused by a small data set with little information about this type of sensors. So, as potential improvements, I mainly suggest to collect more data points, examine the correlation with the temperature, and construct more features. Also, the rejection of unreliable predictions using uncertainty estimation with Bayesian analysis will be beneficial. Okay, so that's it. Thank you.